Okay, welcome back. Here's the next thing we'll do with polynomials. So I want to talk about something called Taylor's formula. But before I do this, let's just quickly recall what operations we have defined on polynomials. So given two polynomials, we had the following things. We could take, say, if f and g are polynomials, we define what the sum means. We recall what the product of those two polynomials means, right? And well, there's another thing we could do, which is a substitution. Substitute values for x. So values where x is the variable. So these are more or less the three things we have done so far. You can take sums, you can take products, you can substitute a value for the variable. But there are a few more operations that one can perform on polynomials, and let's start out by introducing two more operations on polynomials. Okay, so one of them is called composition. Of course, again, must be quite familiar. So if f and g, if f of x, g of x are polynomials, you can combine them to get a new polynomial. Their composition, called h of x, is defined to be f of g of x. Okay, so what does this mean? It just means in this polynomial f, wherever you have the variable x, you don't substitute a value for x. Instead, you just substitute the polynomial g of x in place of x, right? So I hope this is familiar from something you have seen before. Now this is called the composition of f and g. So sometimes this is written as f circle g of x. Okay, this is just notation for this. So this is sometimes written like this, f circle g. And a key thing to note is that composition very much depends on the order in which it is performed. So f of g of x may not be the same as g of f of x in general. So f of g of x need not be the same as g of f of x in general, which means, I mean, could be equal in some special cases, but for arbitrary f and g it will not be the case that they are equal. Okay, so let's just do an example of composition just to get a feel for its basic properties. So if I have f of x is x squared plus x plus 1, it's a degree 2 polynomial. G of x is x cubed minus 2, so in this case a degree 3 polynomial. Their composition, what's f of g of x mean? It's just you take the polynomial f and plug in this polynomial in every slot. So instead of x, I plug in x cubed minus 2 for f of x. So it's x cubed minus 2 squared plus x cubed minus 2 plus 1. Okay, so that's f of g of x. So one could of course expand this out in full. This is x power 6 minus 4x cubed. There's an x cubed from there, so it's a minus 3x cubed plus 4 minus 2 plus 1. Okay, so if you expand this out in full, this is what it turns out to be. And of course one can similarly compute, in this case, g of f of x to see that in fact it's not the same. Okay. Now what are the key properties of this guy? Observe that degree of f circle g, meaning the composition of f and g, in this case one of them was degree 2, the other was degree 3, and their composition had degree 6. Okay, and this is true in general. The degree of a composition, if f and g, so note, if f and g are non-zero polynomials, if f of x, g of x not zero polynomials, then the degree of their composition is in fact the product of their degrees. Okay, so that is going to be true in general. It is very easy to see. Just leave this as an exercise for anyone who wants to check this. Now, so I talked about composition, it is one operation on polynomials. Here is a second operation, that of derivative. Okay, so again it is the same notion of derivative that you have probably seen in calculus, except on polynomials it can sort of be defined much more simply. It does not require developing a big theory of what the limits are and so on and so forth, but it can just be given by very simple rules in general. So derivatives are much simpler when you are only worried about polynomials. So what is a derivative of x power n, for example? So if I take a polynomial f of x, which is some power of x, so n here is, for us, since it is a polynomial, I am talking about n greater than or equal to 0. The derivative of this polynomial, so denoted, well, you can either call it d by dx of f of x or as f prime of x. So these are both just notations, is just n times x power n minus 1. Okay, so the derivative of a polynomial x power n is just nx power n minus 1. This is the usual rule for derivatives, and what I want to do is sort of see what happens when I keep doing this repeatedly. So this is what you would call higher order derivatives. So observe that all the usual rules for derivatives are of course valid, right? I mean, for me derivative still means whatever it means in calculus. So all the usual rules of derivatives are valid. So in particular, if I take the derivative of a sum of two polynomials, the answer will be the sum of the derivatives. So observe that the rules for derivatives are still the same. So if I take d, or let us call it, if I take f plus g, a sum of two polynomials, and try to find its derivative, then it is just the sum of the derivatives. Or if I take the product of two polynomials and try to take the derivative, so observe the product, taking derivative of a product is given by what is called the product rule, which is you take derivative of the first term, keep the second term as it is, this is the product rule, and so on. So any other rules that you remember for derivatives in calculus, of course all the same apply here, right? You can pretty much feel free to use all the rules. So now observe the following nice thing which happens when you keep taking derivatives of polynomials. So suppose I have a general polynomial, so I just write an arbitrary polynomial has this expression, it's a degree d polynomial, and if you sort of take one derivative, what we call f prime of x, then the derivative of a constant is 0. So it is a polynomial which will start with, well, the constant term now becomes a1, so this is really a1 plus the derivative of this is x square is 2x and so on, dad x to the d minus 1. Now of course you can keep doing this, you take the derivative of the derivative, so this is often what is called the second derivative f double prime, or sometimes just written as f2 of x, okay, where the 2 on top is in brackets. So again when you take a derivative again, the a1 is a constant, so it vanishes, so it starts with the 2a2 plus x square will now again give you 2x as derivative, so this is 2 into 3 a3x plus the next thing will become, let us see, 3 into 4 finally you keep doing this d times, you take a derivative at every step, you keep doing this d times, what you finally end up with is, only this last term survives when you do d derivatives, and the derivative of this taken d times is just AD multiplied by d into d minus 1 into d minus 2 and so on, d minus 1. At every step the power of x will sort of climb down and times x power 0, which is just a 1. Okay, and if you do it once more, since the preceding answer is a constant, this is just going to give you a 0. Okay, so this is sort of the full hierarchy. If you take a polynomial and you keep doing successive derivatives, repeated derivatives to it, what you will get is it will be a degree d polynomial to start with, a degree d minus 1 polynomial, d minus 2 and so on, till finally it becomes a constant or a degree 0 polynomial, and the answer, final answer is just a 0. Okay. So now here comes the here's the problem that we want to solve, which leads to what's called Taylor's formula. Again it shares some aspects with the interpolation polynomial given real numbers. So let me call them C1, C2, so given d plus 1 real numbers, not distinct or anything, arbitrary real numbers, find a polynomial maybe we'll just call it f of x. So here it's sort of nicer to re-index this. So instead of calling them C1, C2 till CD plus 1, let me call them C0, C1 till CD. And you'll see in a minute why. Let's just call these d plus 1 real numbers as C0, C1, C2 dot dot dot. So I want the following conditions to be satisfied. I want my polynomial to have degree at most d, and it should be f evaluated at 0. If I plug in x equal to 0, I want it to give me the number C0. If I take the derivative of f and evaluate it at 0, I want to get the number C1. The second derivative evaluated at 0 should give me the number C2 and so on till the dth derivative evaluated at 0 should give me CD. Okay. So in the interpolation problem, what we were prescribing was some x values and some y values, and wanting a polynomial which will take those prescribed which will take the prescribed y values at those x values. Here it's sort of different. There is really only one x value which is in play, which is the value x equal to 0. At every point what you are really doing is substituting x equal to 0, but what you are now given is various things. You are given the value of the y value at that point, you are given the value of the derivative at that point, you are given the value of the second derivative at that point, and so on and so forth. You are given values of all derivatives but at a single point. In the interpolation problem you are actually given only the values, there are no derivatives involved, you are only given the values but at d or d plus 1 different points. Okay. So but in many ways it's similar, both of them really ask for something like this. You give d plus 1 pieces of data and ask for a polynomial which has those, which satisfies that data essentially. Okay, and in fact it turns out this problem is much simpler to solve than the Lagrange interpolation. So observe that it's more or less all the things we need are already there on the board. If you plug in x equal to 0, so if you take f of 0, then observe that plugging in x equal to 0 will make all subsequent terms 0. Okay. So what you get here when you plug in x equal to 0 is only the very first term, you only get a0. Similarly, if you take the second line, you plug in x equal to 0, all subsequent terms are 0, leaving you only with the constant a1, and second derivative will at x equal to 0 will only give you the constant 2a2. The next guy will give you the constant 2 into 3a3 and so on. So observe that, so this is quite straightforward from what we are doing, that f of 0 is just a0, f prime, the derivative at 0 is just what did we say, 1 times a1, the second derivative at 0 is just 2 times a2, third derivative at 0 is 2 into 3a3, let's just write one more, fourth derivative at 0 would just be 2 into 3 into 4 a4 and so on. Okay. So, in order to make this a little more symmetric, let us just throw in a 1 everywhere. It is 1 into 2, 1 into 2 into 3, 1 into 2 into 3 into 4 and so on. Okay. So, what we gather from here is that in fact these constants a0, the coefficients a0, a1, a2, a3 and so on are just directly obtained in terms of the values of the higher derivatives at 0. So, what do we conclude? So, in fact we conclude that a0 is just a1 is just the first derivative, a2 is the second derivative divided by 1 times 2 by 1 into 2 into 3 1 2 3 4 and so on. Okay. And these denominators are precisely what are called the factorials. So, observe that in general if n is a natural number, n factorial just means the product of all the numbers from 1 to n, and so this is just another way of writing this is, so let us just say aj is nothing but the jth derivative of f at 0 divided by j factorial. Okay. So, this holds for j equals 1 2 3 till d. So, this is actually true for j is 1 2. So, observe from here, first derivative divided by 1 factorial is just a 1, second derivative divided by 2 factorial, third derivative divided by 3 factorial and so on. But in fact one can sort of, just to have a more uniform expression, you can also define 0 factorial as 1. So, here is another, so this definition really is only if n is at least 1, but the usual convention is to define 0 factorial also as 1. So, this can view as a convention, in which case a0 also has the same, is given by the same expression. So, observe this is nothing but you take f, you can view that the function itself as being the 0th derivative of itself divided by 0 factorial, which is a 1. 0th derivative just means you do not do any derivatives, you just leave it as the function itself, and so a0 is, if you wish you can think of it as the 0th derivative evaluated at 0 divided by 0 factorial. So, in fact with this convention this is also true for j equal to 0. So, if you wish you can now change this to say it is true for j going from 0 to d. Okay. So, what does that mean? The jth derivative evaluated at 0 is in fact given, that is exactly what we require to be Cj. So, conclusion is that the polynomial f of x that you want is nothing but, so it is the sum, so I will just use the summation notation, it is j going from 0 to d of so f of x is just given by the sum of its higher derivatives at 0 divided by j factorial times x power j. So, this formula here is what you would call Taylor's formula. So, this is for where f is a polynomial of degree at most d. And this is what is called Taylor's formula. Right. So, this is something that holds in general for any given any polynomial of degree at most d. What we have said is its coefficients can all be obtained in terms of derivatives of the function. So, the function itself can be written back in terms of the coefficients like this. So, just to complete this the solution to the problem that we mentioned, if you sort of are given prescribed what the derivatives are, then you just plug these values in there and you figure out what the function is. So, what is the solution to this problem here? So, the solution to the problem as posed there is the following. that I know what the jth derivative at 0 is. It's given to be Cj. So therefore my function f is nothing but summation Cj by j factorial x power j. This is the function that you want, a polynomial of degree at most d with prescribed higher order derivatives at 0. Okay, so it solves this problem. Now just so one remark here, observe this may not have degree exactly d, because the dth derivative could be a 0. Suppose my Cd is a 0, it means that x power d occurs with coefficient 0. So this could very well have degree smaller than d. So all we can say is at most d is the best we can say, because we do not quite know what this last real number is. Now the other thing here is to observe that, so observe just one more thing, since we sort of talked about the 0 1 idea at some point. If you look at, so let us just think of this as follows. Think of it as Cj multiplied by x power j divided by j factorial. So let me just think of it like this. So you look at this guy, x power j by j factorial. Let us call it a polynomial something, let us call it fj of x. Okay, so for each value of j between 0 and d, I have a polynomial called fj of x. It's a very simple polynomial in this case. It's just x power j divided by j factorial. Now what property does this have? So if I take this polynomial fj and I subject it to say an arbitrary number of derivatives. So I take fj and I say I take k derivatives of fj and I evaluate it at 0. Okay. So my question is, what is this answer? What do I get when I take this polynomial, subject it to k derivatives, I apply derivatives k times and then evaluate the answer at 0. Okay. So observe that here is what happens. If k is smaller than j, if k is strictly smaller than j, then taking k derivatives will give you some constant in front, but there will be some coefficient, there will be some power of x left over, which when you evaluate at x equal to 0 will give you a 0. So this will give you a 0 if k is strictly smaller than j. If k is strictly bigger than j, then here is a polynomial of degree j, but you are taking derivatives far too many times, you are taking derivatives more than j times. So of course the whole derivative itself is 0 in this case, you do not even need to plug in x equal to 0. So if k is less than j or greater than j, it is in fact 0, but if you put exactly, if you subject it to exactly to j derivatives, then this is going to give you j into j minus 1 into j minus 2 and so on each time you take a derivative, and when you plug in x equal to 0 you will get exactly 1. Okay. So let us just rewrite this, fj k of 0 is 1 if k equals j and 0 if k is not equal to j. Okay. So this is again starting to look a lot like what we did in the case of interpolation in the example with vectors and so on. It's sort of like the 0 1 idea. So these polynomials fj's are like the with respect to the operation of taking derivatives. Here it's not, you are not really plugging in, or there is no dot product, but now here the operation is with respect to taking derivatives. Fj has the property that it is most well behaved when you take exactly j derivatives and plug in x equal to 0. When you do anything else, when you plug in, when you subject it to k derivatives where k is not equal to j, the answer is always a 0. Okay. So this is again the 0 1 idea in action if you wish. But here it is much simpler, I mean it would not be particularly illuminating to go this way straight up. Okay, and so there is just one slight variant of this that I want to mention. So here is a variation of this problem. Suppose you are given d real numbers, you want to find a polynomial f of x of degree at most d, which has the following property, that if you take j derivatives, or let us just write it out the same way, if you evaluate f at, there is also a real number a which is given. So the evaluation of f at a gives you c0, first derivative at a gives you c1, second derivative at a gives you C2 and so on till the dth derivative of A gives you the number CD, okay, where A is also some real number. So what is A? A is also some real number given A which is a real number. Okay, and so this is basically, instead of plugging in x equal to 0, what you are doing is really plugging in x equal to A everywhere. And so given all higher order derivatives at the point A, how do you reconstruct the function f itself? So the problem now is find f. Well, that's what's written there, right? Okay, so find the polynomial f. And I'll just leave this as an exercise, which you can more or less do by pretty much following the same set of steps. Okay, so just try copying the same argument that we did with x equal to 0. It turns out there's also a simpler thing that one can do, but anyway, that's something that we'll look at some time.